Hello students, in this lecture we will talk about optical conductivity. Now, this optical conductivity can be derived quite simply from ordinary uh, time dependent perturbation theory. Now, we will first consider a system of block waves. Or uh, Mainly by block we mean conduction electrons, uh, and they are described in the absence of electric uh, field, of which electromagnetic variations by energy eigenvalue psi k of the wave equation. So we can write h0 psi k is equal to minus h cross square by 2m del square plus v, which happens psi k, and this is equal to ek psi k. This is a Schrodinger's equation. Now we now add a weak vector potential A characterizing the radiation field. This corresponds to the radiation field, and this is introduced by an extra term which we will take as h1, the perturbation term, and it is defined as minus IE h cross by MC into A dot del, and this H0 is the 0th order Hamiltonian to which this perturbation has been added. So it's the 0th order. Now this extra term is responsible for exciting transitions. It will excite, cause transitions to take place. An electron in an unperturbed state, suppose that wave function is given as psi k r, which is unperturbed. At time t is equal to 0, this is an unperturbed state of electron, will subsequently has an energy now psi k r t, where t is not equal to 0. This is a wave function, and it will correspond to the eigenstate, say psi k r. Okay, that you already told. Now we can calculate the transition rate between the occupation state psi k and an unoccupied state psi k dash. So our main objective is to find the transition rate of the electrons. So there is an occupied state psi k, and there is an unoccupied state psi k dash. This is occupied is unupright. And we're using time-dependent perturbation theory as told earlier. Now, for a vector potential that varies in time according to its relation, so this wave vector we can express at equal to v is equal to a0 exponential I omega t uh, plus higher term. So we're not considering that. So it is varying. We'll take the first term. So this vector potential is varying in this fashion. The rate of transition accompanied by the absorption of a photon of frequency omega from the radiation period. So it is given as rate of transition that we are finding out, and which is correspond to an absorption of a photon also takes place. So all these phenomena can be expressed as the radiation period q k. It's different right here. Q k k dash, and it is equal to 2 pi by h cross into the expectation value whole square h cross expectation value psi k dash psi h psi k whole square into the delta term the ek dash minus ek minus h cross omega. Now the energy absorbed per unit volume as a result of this transition is given as h cross omega to k dash. The total rate of energy loss is obtained by summing of this over an initial and a final state of all the electrons. So total rate of energy loss is obtained by summing this over the initial and final state of all the electrons over initial and final states of all the electrons. a new factor is introduced, uh, that is given as nk0 1 minus nk0. There's a new factor for this purpose, and where this is nothing but the probability of occupation of the state key. The probability of occupation of state key. We find the total rate of energy loss. From here we find the total rate of energy loss, and so this is also equal to the joule heat loss. And that is given as J dot E, and is being with the summation Ij sigma Ij Ei Ej, where the electric field is I omega A by C. So this has got a real and imaginary part. So if you consider only the real part, so so the real part of sigma I j omega, this is equal to 2 pi e square h cross square divided by m square omega into summation over k dash into expectation value of psi k sigma I psi k and dash multiplied by sigma k dash j sigma k expectation value of this multiplied by this factor nk0 1 minus nk0 into delta function of ek dash minus ek minus h cross omega. So, so this is so initially if you compare it with the previous expression, so here you can see that it is 2 pi by h cross. This expression has been rewritten in a different form here. Yes, it is written in a different form here. You can see this is how it has been written, and with this factor introduced, and sigma ik, the whole square has been replaced by 1 corresponding to I and 1 corresponding to the j at p. And this is the basic formula for the real part of the optical conductivity. So this is actually, we are finding out this optical conductivity, and this is the real part, and the imaginary part of the conductivity is given by Cramer's chronic relation. So this optical conductivity is imaginary part is given by Cramer's chronic relation. Cramer's relation, and we use a formula called a Cubo formula. uh, where we write sigma k as exponential minus beta h cross omega divided by duration exponential minus beta ek is resistivity, and it is actually equal to the exponential. So this will be exponential minus beta e k divided by the trace, that means the sum of the diagonal elements, uh, into exponential minus beta pk, where beta is equal to 1 by beta t. This is the Boltzmann's constant, and we get j0 as equal to minus ie h cross nil by m is the quantum mechanical current density operator. So this is the quantum mechanical current density